That is, it's too big. Okay, so to get the initial interval here, you're going to do ratio test. Okay, and without doing all the intermediate steps, this basically becomes after you simplify everything and take all the limit, you get 4x. So the negative ones in this absolute value becomes 1. The square root of n plus 3 over square root of n plus 1 plus 3, that limit is 1. So you basically just have 4x. We need that to be less than 1. That's what the ratio test says. If that limit is less than 1, then you have convergence. So this becomes negative 1 is less than 4x is less than 1. So our initial, the interval itself is negative 1/4 to 1/4. But then we have to check the endpoints. So we're going to start with negative 1/4. When you put negative 1/4 in here, you get negative 1 to the n, 4 to the n times negative 1/4 to the n. Okay, so 4 to the n times negative 1/4 to the n is negative 1 to the n. So all this right here, so you think about, you have n 4's multiplied together, n negative 1/4 multiplied together, so you could pair them up. You could pair up a 4 with every negative 1/4, and you'd have n of those pairs, and all those would would multiply to negative 1. So that's essentially negative 1 to the n. And then negative 1 to the n times negative 1 to the n is just 1. It's just 1 because you have n negative 1s and then n negative 1s, and then if you multiply all those together, you just get 1. So that when x is negative 1/4, this whole thing becomes 1 over square root of n plus 3. Which is not alternating. It's just 1 over square root of n plus 3. So when x is negative 1/4, you have 1 over square root of n plus 3. Is that a convergent or divergent series? It's a lot like a p-series, right? It's a lot like a p-series. It's just slightly less than a, but not, so the plus 3. So when n gets large, the plus 3 is insignificant. It has no bearing on the problem. So really we have a divergent p-series because n is 1/2. So that's divergent. So we're not going to include negative 1/4. When you do positive 1/4, what happens? When you have positive 1/4, then you get a negative 1 to the n term on the top. So, or 1/4. Oh no, so that's 1 to the n. So this thing in blue is 1 to the n, which is 1, and you still have the negative 1 to the n. So now when it's positive 1/4, you have that same series but now alternating. That same series but alternating. Divergent or convergent? That's convergent by the alternating series test because the 1 over square root of n plus 3, it decreases and it goes to 0. Because it decreases and goes to 0, any sequence that decreases and goes to 0 and then alternates is convergent. That's the alternating series test. So we are going to include 1/4. So your final answer is -1/4 to 1/4, and you're going to include 1/4. Because when you do -1/4, you essentially get a divergent p-series. When you do positive 1/4, you get a convergent alternating series. It's the same piece, basically the same p-series or close to it, but it alternates, so it converges. Questions on that example? Okay. So if I could, I know number 1 was tough because you had to get them all right to get it. So if I can, I'm going to go through it fast. It'll be on the video. I'll just go through these fast, okay? So number 1, this right here, cosine n pi, is exactly the same as -1 to the n. It goes -1, 1, -1, 1, -1, 1. Okay? So because a cosine is a periodic function, it can be manipulated to just be alternating -1 and 1, just like -1 to the n. So what do we have? This is going to be convergent by the alternating series test because 1 over ln of 7n decreases to 0. It alternates. So that's D. Next one. Next one looks like, so it's kind of geometric-ish, right? Geometric-ish, this 15 to the n over 4 to the 2n. But it's not quite geometric. It's also times n plus 1. So we could compare that to a geometric series. Compare that because it's almost a geometric series, but it's times n plus 1. So we're going to compare that to a geometric series. All right, next one. What is this like? When n gets really, really large, you basically get 1 over n squared, which is like a p-series. So we're going to compare that to a p-series. Okay, next one. That is an alternating series. It's not a p-series. It's not geometric, but it alternates, and since it decreases, this is very similar to the alternating harmonic series because it's like 1 over n, kind of. So that's alternating. That's just a plain old geometric series right there. Number 5, that's geometric. 4 to the n over 8 to the 2n, geometric. What's this? Okay, square root of n over n is similar to 1 over the square root of n. So so if n gets very, very large, it basically becomes 1 over the square root of n, because that's what square root of n over n is. It's like if you rationalize the numerator, you get, and that's similar to what we just saw in your example. So that's alternating series that converges. Questions on any of those? I did them fast, but we don't want to. I know it. Any of those you have a question about? Okay, so it'll be on the video if you can pause it and think about what I said. But we want to move on to the new stuff. Okay. So what we saw with these power series is they're kind of like a polynomial function, right? These power series, they're kind of like a polynomial function with an infinite number of terms, right? Because they got an x in them. And we found the values of x for which they converged, okay? So these series can be ways of writing functions. So let's recall this, the geometric series is a over 1 minus r when r is between -1 and 1. So let's look at this function. 1 over 1 minus x. What does that kind of look like? 1 over 1 minus x. What? Yeah, a over 1. So you should be noticing, oh, that's a lot like a over 1 minus r. What's a? 1. What's r? X. So we can write 1 over 1 minus x, since it's a over 1 minus r, we can write it as an infinite sum. See if you can do that. So rewrite 1 over 1 minus x as an infinite sum by seeing that 1 over 1 minus x as a over 1 minus r. So what would it be as an infinite sum? Right, so we're saying, okay, what if that were 1 over 1 minus x? Then what would this be? That's what we're saying. If this were 1 over 1 minus x, then what would this be? Write it down. Go, write it down. So we could say 1 over 1 minus x equals what sum would it be? So you got it? Agree? It'd be x to the n, right? 1 times x to the n. Okay? Well, what's that? You see that and you think what? Write it out. You see that and you think what? Write it out. Then we also have to ask the question, I said that equals that, but for what values of x is that valid? Okay, so when you wrote that out, you should have gotten 1 plus x squared plus x cubed, etc., plus x to the 4th plus x to the 5th. Okay, but that's only true when x is in what interval? So that's not true for all x. It's only when x is, well, x is our r value, and so for what values of r does the geometric series converge? -1 to 1, right? -1 to 1. So notice, so we've got this function, 1 over x, 1 over 1 minus x. And by seeing it through the lens of a series, it's equal to this infinite polynomial. But only from -1 to 1. Okay, only from -1 to 1. So what happens is, as you continue to add more and more of these terms, this polynomial continues to do a better and better job of approximating 1 over 1 minus x in the interval -1 to 1. So let's look at that. It's pretty cool. So are we good with the basics here? Does it make sense? Anybody have a question? Okay, so here I've set up that thing, n equals 0, x to the n, right? But then I'm saying I'm gonna take partial sums, meaning I'm gonna only go up to some value j. So right now j is 0. So when j is 0, if I go from n equals 0 to 0, then what do I get? What is that sum? So n equals, so right now the value of j is 0. Let's do it. Let's do it. Let's make it a little clear here. Okay, that's better. Okay, so now capital N is where I'm going to sum up to, right? So I'm just going to take the first capital N terms. So right now, capital N is 0. What is the sum? Just 1, right? X to the 0. That's all you get, just that one term. And so what do we get? We get y equals 1. So the red graph is the actual graph of 1 over 1 minus x. And now the purple graph is our summation when I just have n going from 0 to 0. Just the first term, 1. So is it approximating 1 over 1 minus x? Well, is it doing a good job approximating? No, but it is right about one thing. What is it right about? Yeah, it's got this 1 point right? 0, 1. It's got that right. So now what I'm going to do is I'm going to make n, when I make n, capital N equal to 1, then what will my terms be? When I make capital N equal to 1, then I'm going to have n equals 0 and n equals 1. So it's going to be 1, then what? Plus x. So I'm going to do that. I'm going to make capital N equal to 1. And let's see what we get. So it still has the intercept right, but it looks like it has something else right too. What else does it have right now? What's the same now also besides the intercept about our two graphs? Now that I've added one more term to the sum. It's what calculus is all about. 3 important words. Rate of change, right? So not only is the intercept right, but it looks like the rate of change of our new graph is the same as the rate of change of the 1 over 1 minus x. So now I'm going to make n equals 2, and the sum will be what? 1 plus x plus? So when I make capital N equal to 2, I get the first 3 terms. Remember that the red graph is the true 1 over 1 minus x. And now the purple one is 1 plus x squared. And so what's happening? Every time we add a term, here's 1 plus x squared plus x cubed. Yeah, so this polynomial, this like infinite polynomial, as I add more and more terms to it, it's like converging on the actual graph of 1 over 1 minus x. Such that if I were able to add all the terms, all infinitely many terms, I would get the actual graph 1 over 1 minus x between -1 and 1. So let's add another one here. That's the first 5 terms up to x to the 4th. Then x to the 5th. X to the 6th. Okay, so now you can see around, for some interval here, from about 0.7 to about 0.8, it's black. It's just like almost right on top of it. Doing a really good job for most of the interval. Okay, so this is adding up to x to the 7th, x to the 8th, x to the 9th. So just the first 11 terms does a really good job of estimating the actual graph of 1 over 1 minus x. So imagine if we added the first 100 terms. Let's do it. So I can just change this to Okay, so but we only need to show this from -1 to 1. And now it's like this is the first 100 terms, or all the way up to adding x to the 100th, and it's like they're to the naked eye you can't see the difference, right? There's no daylight between them. So if we were able to add all infinitely many terms in that polynomial, we would have the graph of 1 over 1 minus x between -1 and 1. And we showed that's true because through the fact that by looking at this as a geometric series. So there's kind of a theme here that, and we'll talk about this for the next couple of days, that polynomials, if you have polynomials, you can approximate any function with a polynomial. It's just as long as you have enough terms in your polynomial. So, and those polynomials are formed by infinite series. And so any graph we can estimate with an infinite polynomial, okay? But the ones we're going to work on to start with are just these ones that look like a over 1 minus r. So a very narrow class. So next week we'll be able to write any function as an infinite polynomial, but we just start with this very narrow class of functions that look like a over 1 minus r. Okay. Doesn't make sense. Okay, so here's a more complicated one. X over 2x squared plus 1. Can we write that as a power series and find the interval of convergence? So again, we've got to make that look like, in order to make any progress, it must look like a over 1 minus r. See if you can do it. So you got to change the form of that thing so it still is the same function, but it looks like a over 1 minus r. Then you can write it as a geometric sum. So what over 1 minus what? What over 1 minus what? That should be hopefully not too hard. So we're saying what is a? Too easy, right? X, okay? What is r? If it's a over 1 minus r, and we have 2x squared plus 1, that's 1 minus what? He wants negative 2x squared. That's it. And now we can write that as a geometric sum, and then we can figure out for what values of x this equality is valid, right? It's not going to be for all x. It's going to be for x for which this series converges. Okay, so we're going to go from n equals 0 to infinity. It's going to be a r to the. So, how many got that much before I started writing? Hopefully, at least some of you. That shouldn't be hard, right? So you're changing the form into a over 1 minus r, and then applying a r to the n. Now we want to get this to look like something we're more familiar with working with here, because we got some things we can simplify. So really we have x times negative 2 to the n times x squared to the n. And what is x times x squared to the n? We can combine all that together. X to the what? So hopefully, we gotta know our rules of exponents pretty well here. X squared to the n times x. Nope. Yeah, so you have 2n x's multiplied together, and then one more x. So 2n plus 1. Okay, and then we have negative. Sometimes it helps just to get the alternating thing by itself. So just negative 1 to the n, that makes it alternate, and then we also have 2 to the n. So negative 1 to the n, 2 to the n. Okay, so what's the interval of convergence? Interval of convergence is, how are we going to find it? So we just have a power series now, right? We have a power series, and that power series is going to estimate that, or it's going to equal that function if we could take the whole thing. If you take the whole power series, it equals that function for certain values of x. How do we find those certain values of x that it works for? What are we going to do? We're going to do the ratio test, right? N plus 1. It's going to be now we're experts at this. Once I get that power series, now we've done all this before. So that limit, so this is going to go away. That limit is going to be, that'll just be 2, and this I think we're going to have x squared, right? It's going to be 2n plus 3 and 2n plus 1. So we end up with 2 more x's on the top, so we get 2x squared. Did I do the math right? I get a 2 from this, and I get an x squared from this, because this is going to be 2n plus 3, meaning 2 more x's multiplied together in the numerator than in the denominator, leaving me x squared. So when is 2x squared? We want to find the x for which 2x squared is less than 1. When is x squared between negative 1/2 and 1/2? Other way around. So then x could be, so really that's always going to be greater than 0. So, but still x could have negative values when squared will be between 0 and 1/2, and that will be a square root of 2 over 2. So those x values from negative square root of 2 over 2 to square root of 2 over 2. This thing will converge. We need to check endpoints, but for time's sake, we won't. You've done that before. But this is the basic interval before checking the endpoints. So for those values of x, that power series is going to be the same as that function x over 2x squared plus 1. Anybody have a question? Yes, please.
Could you explain why it's negative radical 2 over 2
Yeah, so x squared is going to, so this would be the same as saying 0 is less than or equal to x squared is less than 1/2, right? Because x squared is only going to be positive. But x could be negative, and then when you square it, it will be in this range. Right? So x can still be negative, and then it'll just end up being in the positive 0 to 1/2 range. So this is just going square root, and square root. So square root of x squared is x, square root of 1/2 is radical 2 over 2. But negative values of x will, when squared, will fall in this region. So we still want to include negative values. Does that answer it? Was that your question also? I'm not taking the square root of negative 1/2. For x squared to be, x squared is always going to be greater than or equal to 0. Okay? So this is the exact same thing as writing this. Because I'm never going to get x squared to be negative. Okay? So for x squared to be less than 1/2 would be, x is going to be between 1/2, square root of 1/2 and negative square root of 1/2. Because negative values of, say, like negative 0.1 is in this range. So if x is negative 0.1, you square it, it's between 0 and 1/2. Is that the same question over here?
My question was just square root of 1/2 to
It's the square root of 1/2. It's that's 1 over square root of 2 is the same as radical 2 over 2. Yeah, I just rationalized the denominator on the fly there. Yeah, so this is the same as square root of 1/2. Okay, other questions? Okay, so something different just to think about before we leave. How about this? So the thought here is we could multiply this out. And then r would be 2x minus x squared. But then let's think about that. Then we'd have 3 times 2x minus x squared to the n. And what's that going to mean for large n? What happens? The bigger that n gets, the more and more terms. This is the binomial expansion, right? So if n was 100, so just in the 100th term alone, you would have 100 things summed together just when n was 100. So now think about when n is 1,000,000 or 1,000,000,000. Every increasing n by 1 means you have, for that nth term, say n is 100, that's going to be itself like 100 terms. And then when you get to n equals 1,000,000, that itself will be 1,000,000 things added together, just for when n equals 1,000,000. Not to mention when it was all the things leading up to that. So this is not good. Okay, we don't want to do this. So we need something else to make sense of this. You never want to have a binomial or more things to the n, because you think about large n. We want one term per n value. So we want one term per n value, not increasingly many terms for every n value. Okay? So just as a preview, we're going to look at this instead. We know how to do that. What could we do to this to get something like this? Think calculus. What could I do to 3 over 1 minus x to get something like 3 over 1 minus x squared? Think calculus. How does that relate to that, generally speaking? This is kind of like the derivative of this. Do you see that? And if we have polynomials, derivatives of polynomials are easy, right? We're talking about, if I could write this as an infinite sum right here, an infinite sum of monomial terms, like a polynomial, the derivative is easy, right? You just go one at a time, and you take individual derivatives of the terms. So that's a preview of things to come. So to get this, we're actually going to start with something like a over 1 minus r, and once we get that set, we're going to take the derivative of it. When we take the derivative of it, the derivative will be like what we want.